All right, let's get started. So the plan for today is to finish up the material we didn't cover in the last lecture on autoregressive models, and then we'll talk about learning. So towards the end of the last lecture, we talked about RNNs as being another way to parameterize autoregressive models. And remember, the key idea is that you have a small number of parameters, actually a constant number of parameters with respect to the length of the sequence you're trying to model. And you're going to use these parameters to basically keep track of the context that you use to predict basically the next token or the next pixel. And you keep track of all this information through a single kind of hidden vector that is supposed to summarize all the information that you've seen so far and that you're going to use to make the next prediction. Like in this example here, where I'm looking at, let's say, building an RNN to model text. So you have tokens, and you might have some prefix, like my friend opened the, and then you're going to use all this information. You pass it through your RNN, and the RNN will update its state, its hidden vector, and you end up with a hidden vector H4 here, and then you're going to use that vector to predict the next token. And maybe if you're doing a good job, then you'll put high probability to reasonable ways to continue this sentence, like the door or the window, and you're going to put low probability to things that don't make sense. And as we've seen, these RNN models can work reasonably well, even if you build them at the character level, which is pretty hard. One challenge is that this single hidden vector that you have here basically has to summarize all the information that you've seen so far. And that's the only thing you can use to make the next prediction. And that can be a problem because you kind of like have to do a pretty good job of summarizing the meaning. Or let's say if you're building a language model, this single vector has to capture all the entire meaning of all the previous elements in the sequence, which can be challenging. The other problem of RNNs is that basically you have to unroll the computation if you want to compute these probabilities and you want to come up with reasonable losses at training time, which makes them pretty slow and pretty hard to train. And the other problem is that, they can be a bit problematic to train because you have these long dependencies from, let's say, early on in the sequence towards the, let's say, the present. It can take many updates to get there, and this can lead to exploding or vanishing gradients, and it can be problematic. So this is now what's actually been used in state-of-the-art language model, autoregressive language models. Existing state-of-the-art models use attention. And the basic idea is that they look more like a NAID or like a MAID, these other models that we've seen before, where you essentially are able to use the entire sequence of inputs up to time t to make the next prediction. And so instead of just using kind of like the hidden vector corresponding to the last time step to make the prediction, you kind of like look at all the hidden vectors from previous time steps to predict what's going to come next. And the way to make this effective in practice is to use an attention mechanism to kind of like try to figure out which elements of this sequence are useful and which ones are not, which one you should pay attention to, and which one you shouldn't pay attention to when you make a prediction. And so roughly at a very high level, the way these methods work is that there is some kind of attention mechanism that will tell you how relevant a query vector is with respect to a key vector. So this is similar to when you search in a database, you have a query, you have a set of keys, and you want to figure out, you want to do retrieval. This has a similar flavor, and it will basically tell you how relevant is the hidden vector, let's say, corresponding to the first time step with respect to the hidden vector that you have at the current time step. And this could be something as similar as just taking a dot product between the two vectors. Once you have these similarity vectors, then you turn them into an attention distribution, which is the thing that we were talking about before, the thing that tells you which elements of the sequence matter and which ones don't. And one simple way to do it is to just take all these attention scores and pass them through a softmax to get an actual distribution. Yeah.
Are we not assuming any computational independence?
So the question is whether this kind of model assumes conditional independence. If you build a model like this, again, there is no conditional independence explicitly stated, because in principle, as long as this is just an autoregressive model and we're just parameterizing the conditionals using a function that has a very specific functional form. And so we're not going to be able to capture all possible dependencies, but we're not explicitly making any conditional independence assumption so far. Well, that's if you were to make conditional independence assumptions, yeah, typically performance would drop significantly. As we'll see, the nice thing about this kind of architecture is that it allows you to take into account the full context when you make a prediction, while at the same time being selective and kind of like be able to ignore things that are not relevant and pay attention to things that are relevant. For example, in this kind of simplified version of an attention mechanism, what you could do is you could take an average of the hidden vectors that you've seen before in your RNN, and you weigh them with the attention distribution scores that you have, you average them, and you get a new vector that then you're going to combine with the current vector to make a prediction for the next token. And you see that now we're no longer bottlenecked. We're not just using this green vector to make the prediction, we're able to use the whole history. So we're able to really compare every pair, essentially, of token in the sequence. And that's pretty powerful. And as you can see, for example, in this little example here, I have a robot must obey the orders given, it, and then you need to make a prediction. And if you want to make a prediction, you kind of need to figure out what it refers to. And the attention mechanism can help you to figure out that this it is probably referring to that when you're trying to figure out what it means, you should pay attention to these two tokens, a robot. And so that's sort of like the flavor of why this kind of attention mechanism is helpful, because you can take advantage of the whole sequence. As usual, in practice, you need to be careful about making sure that the model is autoregressive, so you cannot pay attention to future vectors when you do these kind of things. And so you have to use a mask mechanism, just like in these other models, so that you can only basically pay attention to the tokens or the random variables that come before it in the sequence, in the ordering. The other thing that is important is that in an actual system that is used in practice, you would not use any sort of like recurrent architecture. So you wouldn't even need this kind of like recurrent computation here, where you update the state recursively using an RNN. You just use feed-forward computation. You stack multiple layers of attention. And the key advantage of this is that we're back to kind of like the previous made-like setting, where you can actually evaluate the architecture in parallel. So you can kind of like do the computation necessary to make a prediction at every index in parallel across indexes. This is a training time, of course. And this is really what makes these models good in practice compared to an RNN. I think actually an RNN would be reasonably good in terms of modeling power. It's just too slow to train. And these transformers, because they allow for massive parallelism, and we'll come back to this when we talk exactly how these models are trained, but the key advantage is that you can basically evaluate the loss very efficiently without having to enroll the recursion corresponding to an RNN. And that's one of the reasons they've achieved this great success in practice, is because they can be evaluated in parallel, they can take advantage of GPUs, and you can scale them to very large sizes. And you can see some of the demos of the systems that, like the GPTs, GPT-2, 3, 4, that we've seen in the first lecture, the amazing LLMs that everybody's talking about, Llama, other systems that are available online you can play around with, are essentially based on this kind on this kind of architecture. Autoregressive models using this kind of self-attention mechanism that we're going to talk about more in one of the sections that is going to be dedicated to neural architectures. So this is kind of like the high-level idea of one of the key ingredients that is behind state-of-the-art language models. Cool. Now, back to RNNs. People have been using them to not only for text, you can use them to model images. So you can just think of an image as a sequence of pixels. You can generate them in top left to bottom right, one at a time. And you can use an RNN to basically model all the conditionals in your autoregressive model. So each pixel, you're going to have one conditional per pixel, giving you the distribution of that pixel, given all the ones that come before it in the sequence. And each conditional is going to be a categorical distribution over the colors that pixel can take. And if you're modeling pixels using an RGB encoding, then you have 3 channels, red, green, and blue. And so you need to sort of capture the distribution over the colors of a pixel, given all the previous pixels. And one way to do it is to use an autoregressive structure, kind of like inside every pixel, every conditional defining the pixel. So a pixel is going to involve 3 random variables: the red, the green, and the blue channel, and you can generate them, let's say, in that order. So you can compute the conditional probability of the red channel given the previous context. Then you can do the green channel given the previous context and the value of the red channel, and so forth. And in practice, you can basically use an RNN style architecture with some masking, the same kind of masking we've seen in MADE that enforces this kind of ordering. So that first, you try to compute the conditional probability of the red pixel, and that can depend on everything you've seen before, but you cannot peek. You cannot look at the green channel or at the blue channel. When you try to predict the green channel, it's fine to look at the value of the red channel for that pixel, and so forth. And so again, it's basically the same idea, but you're going to use some sort of masking to enforce autoregressive structure. And this was one of the, these are some examples of the kind of results you can get from an RNN at the pixel level, trained on ImageNet, downscaled ImageNet. Again, you can see that these results are not great, but they're pretty decent. Like what you see here is you take an image, you see at the rightmost column is an actual image, and then what you do is you can remove the bottom half, and then you can let the model complete. So it's similar to a language model. You have a prompt, which in this case is going to be just the top half of the image. And then you let your autoregressive model generate the next pixel, and then the next pixel, and then the next pixel, and so forth. And you can see that it's coming up with somewhat reasonable completions. Kind of like has the right structure, it has the right symmetries. It's doing a reasonable job at capturing the dependencies between the pixels. There is some variability in the samples, like here, this one versus this one. Of course, there is stochasticity, so if you sample from even given the same initial condition, if you sample, there is randomness in the way you sample, so you can generate different completions every time. Every time you sample, you're going to get a different possible way of completing that image. And you can see that they have, not always, some of them don't make a lot of sense, but some of the completions are actually decent, and there is some variability, which is good. The challenge is that, again, because you have to evaluate the probability of an image sequentially, you have to unroll the recursion. These models are very slow. And so in practice, what tends to work much better on images is convolutional architectures. These are the kind of architectures that work well when you're building classification models. And so it would be natural to try to use a convolutional architecture to build a generative model of images. The challenge, once again, is that you need to make sure that the model is consistent with an autoregressive one. So what you need to make sure is that when you make a prediction for a pixel, you only use information that is consistent with the ordering you've chosen. So if the ordering is, once again, from top left to bottom right, when you make a prediction for this pixel, it's fine to use information for all the shaded area in the image, but you cannot peek. You cannot look at information coming from the future or coming from any of the white kind of region of the image. And the way to do it is, once again, relatively simple. It's always masking at the end of the day. So when you think about if you want to enforce autoregressive structure, one way to do it is to set up the kernels of your convolutions to be consistent, to have zeros in the right places, so that the way the computation occurs is consistent with the autoregressive nature of the model. So if you have a simple 3x3 kind of convolutional kernel and you zero out all these entries in the kernel, then if you look at the computation graph, whenever you make a prediction for this red pixel, you're only going to use the blue pixels to make that prediction. And so that's consistent with the ordering that we had before. So again, it's very similar to MADE, it's very similar to transformers or self-attention. You basically mask to make sure that things are consistent with the ordering.
I was wondering, with regards to the difference between the RNN and the convolutional approach, try to make transformer with self-attention over the pixels. Do you recover something like a convolutional structure where you get more attention for the pixels in the neighborhood?
Yeah, so the question is whether you can use, I think, attention or self-attention for modeling images, and whether that would recover kind of like the right inductive biases. And yeah, you can use masked, once again, attention on images, and there have been autoregressive models that are essentially using the transformer-like architecture on images, and they've been very, very successful. As far as I know, they're not in the public domain, so these have been built in industry, but they have not been actually released. I think they tend to be more computationally intensive to train, and so other models seem to, like diffusion models that we're going to talk about later, tend to work better in practice. But there's been reported in the literature some good success using transformer-based architectures on images.
How do you model autoregressive architecture for data that's not like very clearly sequential? So like whatever language model is always token, but like in generating an image, is this a matter like how we're actually starting off, like the order that we're doing?
Yeah, that's a great question. The question is, what's the right ordering for images? For text, maybe left to right seems reasonable, but for images, what's the right order? That's a great question, and we don't have a great answer. Right now, the typical ordering is top left to bottom right, but as you said, it's probably not the right one, and you could imagine a different kind of mechanism. There are people, and there's been research where people have tried to learn the optimal ordering. Like you can imagine, there's a combinatorially large number of orderings, but you could try to somehow set up an optimization problem where you search for the right ordering first, and then you find the autoregressive model consistent with that order that maximizes the data fit with moderate kind of success. And incidentally, as far as I know, even for language, you can model right to left, and it works okay too. So maybe the ordering is not that important even for language.
Even if we're using a CNN right now, since it's autoregressive, if we're trying to evaluate the likelihood of, say, an image, don't we still have to unroll the chain rule and result in a really long computation?
So the question is whether these kind of convolutional models can be evaluated in parallel. And to some extent, convolutions can be evaluated pretty efficiently. Convonets can be evaluated it's basically just matrix multiplications, and they can be done very efficiently on modern hardware. In fact, that's another way to build very efficient kind of like language models, is actually based on convolutions, 1D convolutions. You can get pretty close to transformers-like models using convolutions that are, of course, they need to be causal, so you cannot look into the future. You can only look into the past. But using kind of like convolutional models has shown to work reasonably well on language as well. It kind of like matches the performance of transformers models. So that's another way to get fast parallel kind of like computation and reasonably good kind of like modeling performance.
Like the data training problem, like fundamentally different from this, because I guess in any, like in math pixels in between and use outside context to come.
Yeah.
I'm curious if you pre-train with you can still generate, or if that's only applicable to the case where you have only certain masses.
Yeah, so the question is, whether you could train a generative model based on in-painting, where you maybe mask out parts of an image and you train a model to predict the remaining parts. And in general, that wouldn't give you a generative model, although there are ways to generate samples from that kind of architecture, because in some sense, it's still trying to learn something. You need to learn something about the joint if you want to do well at that, but it doesn't give you directly a way to generate samples, at least left to right. You would need to use more expensive, kind of like sampling procedures that make these models harder to use in practice. Although there are variants like masked autoencoders that are used generatively, but that's a little bit more complicated.
Obviously, transformers, they're very good for parallelization, but ignoring the kind of the computational efficiency, just in terms of the raw kind of the representation power of these models, can we say that transformers, the representation space, like you can, is more powerful than LSTM-based models? Say that.
I think that would be hard to claim. So the question is whether transformers are more powerful than an RNN. And I think that's a little bit tricky because an RNN by itself is already Turing complete in general, so it can implement any function. A relatively small RNN, in theory, could do that. So it's been proven that they are essentially arbitrarily. Yeah, so it's really probably more about the efficiency of training, or maybe inductive biases, than there is not a good understanding about the flexibility by itself.
Why would anyone be using an RNN today versus like a transformer architecture?
The question is, why would you use an RNN? One advantage is that then at inference time, keeping track of a single state is actually pretty good because you don't have to do a lot of computation over and over. If you had a vanilla kind of model where nothing is tied, like you might need to do a lot of computation at inference time. An RNN is kind of nice because all you have to do is you keep track of a small state and you can throw away everything. All the past doesn't matter. You just need to keep track of the hidden state, and you just keep unfolding the computation. I mean, it's sequential, but all these models are sequential anyways. But the fact that you have this very small vector, and that's the only thing you need to keep track of with respect to the state, is very appealing. So that's why people are trying to actually get back to RNN-like architectures, because they could be much more efficient at inference time. Cool. So yeah, this is then the other thing you have to keep in mind is if you do this mask convolution, is that you might end up with this kind of blind spot thing, where if you look at the receptive field that you get when you use kernels that are not that are masked, when you make if you have like a stack of convolutions and you make a prediction for this pixel, you're not actually going to take into account these grayed out pixels because of the blind spot. Like if you see what happens if you recurse on this kind of computation structure and you do a bunch of convolution one on top of each other, you end up with this blind spot. And so there are some other tricks that you have to do at the level of the architecture to basically combine multiple convolutions with different kind of masking to kind of solve that sort of issue. And here you can see some samples. It tends to work well. If you replace the RNN with a CNN, you get significantly better samples, and it's much faster. And right, maybe let me. And these models tend to actually not only generate reasonable samples, but they seem to get a pretty good understanding of what is the structure of the images that they see at training time. And one indication that is indeed the case is that you can use them to do anomaly detection. So you might have heard that machine learning models are pretty vulnerable to adversarial examples, adversarial attacks. So you take an image like this one that would be classified as a dog image, and then you add this noise, you get back an image that looks identical to the original one, but would be classified with very high confidence by state-of-the-art models to be something completely wrong. So these two images are different, but in very subtle ways. And there is a natural question of whether you can detect these kind of differences in the images. And if you could do it, maybe you can build more robust machine learning models. And one way to do it is to try to fit in these two types of inputs, like natural images and adversarial attacks, into a pre-trained generative model and see whether they would assign different probabilities to these two types of inputs. if the model is doing a good job, it might be able to detect that this is a natural image. It should be assigned fairly high probability versus this one has something weird is going on here, and so it should be assigned a lower probability. And indeed, a pre-trained pixel CNN model does a pretty good job at discriminating between natural images and ones that have been tampered with. And so what you see here is basically a histogram of the kind of likelihoods. I guess they're written in bits per dimension, but it's the same thing as the probability that the different samples are given by the model is on the x-axis, and on the y-axis is you see how frequently different images, let's say in the training set, are given that probability by the model. And you see that the train and test set, they are kind of here, while the adversarial attack are significantly kind of separated from the natural images, meaning they are assigned much lower probability by the model. And so if you use a threshold to try to distinguish and say, oh, if the probability of my input is significantly lower than what I'm expected to, then I can maybe say that's an adversarial attack, and I can reject it. And these models seem to perform reasonably well, which means that they are no longer getting the kind of high-level semantics of the image, but they really are able to understand the subtle dependencies between the pixel values that exist in natural images. And yeah, question.
People do an adversarial attack if they don't have access to the model.
The question is whether people can do adversarial attacks if they don't have access to the model. To some extent, yes. Depends. There are different kinds of adversarial methods. You can assume that you have exactly know the weights. Maybe you can only know the outputs of the model. Sometimes you don't even have access to anything, and you have to somehow hope that an attack built for a model transfers to a different one. So to some extent, there's been some success even in black box settings.
What makes the autoregressive architecture more robust to adversarial examples?
So the question, the question is whether the autoregressive is it the autoregressive? Yeah.
Pixel defend against adversarial attacks better than other models.
Yeah. So it's not necessarily better. I think the idea is that this is just to show that the generative model, the pixel CNN that was just trained by maximizing the likelihood of a data set, is kind of like able to understand the structure of the images, and kind of like the likelihood itself is useful. So it's not just a matter of sampling from the model, but the likelihood can actually be used to discriminate between different kinds of inputs. And in order to do well, you really need to understand the relationship between all the pixels. You need to figure out that this image is actually different from this image. And so it means that those conditionals that you learn through the autoregressive model are actually doing a pretty good job at discriminating these kind of very subtle differences.
So like for the generative model, how can we evaluate the P it's half? Yeah, how do we know this image is a fake or not?
So you basically just the same thing. I think I have it here. Basically, if you want to compute the probability, you just use the autoregressive chain rule computation. And so you evaluate the probability of the first pixel, the second pixel given the first one, just multiply all those things together, and that gives you the likelihood. That's the formula from an autoregressive model. And you do that for every input image, the same logic, the same function, and then you get different results because the images are different in some fundamental way. Yeah.
Can you explain one more time what the x dimension and y dimension on this graph represent?
Yeah, so the x dimension is like essentially P of x, the probability, the different probability values that are assigned by the model, and it's in bits per dimension because it's normalized by the number of dimensions that you have in the images. But think of it as P of x, rescaled, so that it's a little bit more meaningful. But roughly, it's the probability, and on the y-axis you have the how many images are assigned, it's a histogram. How many images are assigned different probability values. And so you get this kind of Gaussian where even all the images in the training set, they are given different probability values, but roughly they are usually in this range, between 1 and 4. And if you look at adversarial attacks, they are significantly separated. So they're different in probability. Cool, and then yeah, they can also be used for speech, but let me skip that. And the summary is that yeah, autoregressive models are pretty general. They're good because it's easy to sample from them. It's easy to evaluate probabilities, which are useful in itself because you can do things like anomaly detection. You can extend it to continuous variables. One issue with autoregressive models is that there is not really a natural way to cluster data points or get features. We'll see that latent variable models are going to be much more natural for that. Now the next thing is learning, which is going to be pretty straightforward for autoregressive models. You can probably kind of guess how you would train them. You basically, an autoregressive model is just a sequence of basically classifiers, and then you just train all the classifiers the usual way, essentially, right? At a high level, remember, we have your model family, which could be autoregressive models. You have data. To train a model, you have to specify some notion of distance, how good your model distribution is, how similar it is to the data distribution. And we've seen how to define a set of distributions using neural networks. And now the question is, how do you optimize the parameters of the neural network to become as close as possible to the data distribution? And the setting is one where we assume we're given a data set of samples from the data distribution. And each sample is basically an assignment to all the variables in the model. So it could be the pixel intensities, every pixel intensity in each image in the model, or which is the same as a standard classification problem where you might have features and label. You get to see the values of all the random variables. And the assumption is that each data point is coming from the same distribution, so they're all sampled from the same data distribution. So they are identically distributed, and they are independent of each other, which is a standard sort of assumption in machine learning. And then you're given a family of models, and the goal is to kind of like pick a good model in this family, right? So the model family could be all Bayesian networks with a given structure, or it could be fully visible sigmoid belief network, where you can think of a bunch of logistic regression classifiers. They each have a bunch of parameters, and the question is, how do you choose the parameters such that you get a good model? Well, when the only thing you have access to is a bunch of samples from some unknown data distribution. And the goal is to come up with a model that is a good approximation to this unknown data generating process. And the problem is that you don't know what p-data is. Like, I cannot evaluate p-data on an arbitrary input. The only thing I have access to is a bunch of samples from this distribution. And in general, this is pretty tricky because you can imagine samples tell us something about which x's, let's say, are likely under the data distribution, but there is a lot of information that is just loss that we're just losing whenever we just sample from a distribution. All right, so let's say that we're trying to model MNIST again. And so we're, let's say, modeling 784 binary variables, black and white pixels. And what I claim is that this is a really, really hard problem because X is so high dimensional that there is just so many different possible images that even basically regardless how large your training set is, this is a really, really hard problem. Like if you think about it, how many possible images are there? If we have binary variables, you have 784 of them. There is like 2 to the 784, which is roughly 10 to the 236 different images. And somehow you need to be able to assign a probability to each one of them. So let's say that you have maybe 10 million training examples, or 100 million, or 1 billion training examples. There is still like such a huge gap between however many samples you have and all the possible things that can happen. That this is just fundamentally a really, really hard problem. Like this is way more than the number of atoms in the universe. So there's just so many different possible combinations, and somehow you need to be able to assign a probability value to each one of them. And so you have sparse coverage, and so this is just fundamentally a pretty hard a pretty hard problem. And then there are computational reasons. Even if you had infinite data, training these models might still be challenging just because you have finite compute. And so somehow we'll have to be okay with approximations, and we'll still sort of like try to find, given the data we have, we're going to try to find a good approximation. And so the natural question is, what do we mean by best? What's a good approximation? What should we even try to achieve here, given that there are fundamental limits in what we can do? And so the setting, what best means really depends on what you want to do. One goal could be to just do density estimation. So kind of like if you think about the anomaly detection we just talked about, you really care about being able to assign reasonable probabilities to every possible inputs because let's say you care about that. And if you are really able to estimate this full joint probability distribution accurately, then you can do many other things. Then you can condition on a subset of the variables, you can infer the others, you can do basically everything you want. But it's a pretty tall order, it's a pretty challenging problem as we've just sort of seen before. Another thing you can do is maybe you have a specific task in mind, right? If you already know how you're going to use this model, perhaps you can try to train a model that performs well at that particular task. Like if you know you only care about classifying images in spam versus not spam, then maybe you actually want to build a discriminative model that just predicts y given x. Or if you know that you just care about captioning an image or generating images given captions, then maybe you don't need to learn a joint distribution between images and captions. You just need to learn the conditional distribution of what you're trying to predict given what you have access to at test time. That can make your life a little bit easier because you don't think about kind of like density estimation. You're kind of saying, I don't have any preference about the kind of task the model is going to be given. I want to do well at every single possible task. But if you know that there is a very specific way you're going to use the model, then you might want to train the model so that it does well at that specific task you care about. Other times you might care about structure discovery, like knowledge discovery, but we're not going to talk about that in this class. And so we'll see first how to do one, and then we'll see how to do two. And so let's say that really what you want to do is you want to learn joint probability distribution over the random variables that is as good as possible, as good an approximation as possible to the data distribution that generated your data. How do you do that? This is basically density estimation. It's a regression problem, you can think of it, as an estimation problem, because again, you want to be able to assign a probability value to every possible assignment of values to the random variables you have. You're trying to build a model over. And so at this point, really, we just want the joint given defined by the data distribution, which is unknown, but we have access to samples, to be close to this model, to some distribution in your model family, p theta. And so the setting is like this. So there is this unknown p data. There is a bunch of samples that you have access to it. There is a bunch of distributions in this set. Say all the distributions that you can get as you change parameters of your logistic regression classifiers or your transformer model, or it doesn't matter. And somehow we want to find a point that is close with respect to some notion of similarity or distance to the true underlying data distribution. So the first question is, how do we evaluate whether or not two joint probability distributions are similar to each other? And there is many ways to do it. And as we'll see, we're going to get different kind of generative models by changing the way we measure similarity between two probability distributions. There are some ways of comparing probability distributions that are more information theoretic. We're going to see today, like maximum likelihood based on compression, that will give you certain kinds of models. There's going to be other ways that are more based on, if you can you could say, okay, if I generate samples from p data and I generate samples from p theta, you should not be able to distinguish between the two. That would give rise to something like a generative adversarial network. So there's going to be different ways of defining similarities between distributions. And that will be one of the axes, one of the ingredients that you can use to define different types of generative models. For autoregressive models, a natural way to build a notion of similarity is to use the likelihood, because we have access to it. And so we can use a notion of similarity that is known as the KL divergence, which is defined like this. The KL divergence between distribution P and Q is just basically this expectation with respect to all the possible things that can happen. They are all weighted, all the possible things that can happen X are weighted with respect to the probability under P. And then you look at the log of the ratio of the probabilities assigned by P and Q. And it turns out that this quantity is non-negative, and it's 0 if and only if P is equal to Q. And so it's a reasonable kind of like notion of similarity because it tells you, if you somehow are able to choose one of them, let's say P to be P data, Q to be your model distribution, if you are able to drive this quantity as small as possible, then it means that you're trying to make your model closer to the data. And if you're able to drive this loss to 0, then you know that you have a perfect model. And well, I have a one-line proof, but I'm going to skip it, showing that it's non-negative. The important thing is that this quantity is asymmetric. So the KL divergence between P and Q is not the same as the KL divergence between Q and P. In fact, the KL divergence, if you use one versus the other, it's going to give us, both are reasonable ways of comparing similarity. One will give us maximum likelihood training. One will be more natural to, and will come up again when we talk about generative adversarial networks. It's going to be harder to deal with computationally, but it's also like a reasonable way of comparing similarity between P and Q. Yeah, so they're symmetric. And the intuition, as I mentioned before, is this kind of quantity has an information theoretic interpretation. And it kind of like tells you something to do with compression. So the idea is that when you're building a generative model, you're essentially trying to learn a distribution. If you have access to a good probability distribution over all the possible things that can happen, then you also have access to a good way of compressing data. And essentially, the KL divergence between P and Q tells you how well compression schemes based on P versus Q would perform. And so specifically, it's telling you if the data is truly coming from P and you use an optimization, a compression scheme that is optimized for Q, how much worse is it going to be than a compression scheme that was actually based on the true distribution of the data? So intuitively, as I mentioned, knowing the distribution that generates the data is useful for compression. And so imagine that you have 100 binary random variables, coin flips. If the coin flips are unbiased, so 50-50, heads, tails, then there is not much you can do. The best way to compress the result of flipping this coin 100 times is to basically use 1 bit, let's see, 0 to encode head, 1 to encode tails, and on average you're going to use 1 bit per sample, and that's kind of like the best thing you can do. But imagine now that the coin is biased. So imagine that heads is much more likely than tail. Then you know that you are going to, out of these 100 flips, you're expecting to see many more heads than tails. So it might make sense to come up with a compression scheme that assigns low short codes to things that you know are going to be much more frequent. So you could say that you could batch things together, and you could say sequences like HHHH are going to be much more common than sequences like TTTT. And so you might want to assign a short code to sequences like that are going to be frequent, and a long code to sequences that you think are going to be infrequent, and that gives you two savings in practice. So an example that many of you are probably familiar with is Morse code. That's a way to encode letters to symbols, like dots and dashes. And if you think about it, there is a reason why the vowels like E and A are assigned these very short kind of codes, while a letter like Q is assigned a very long kind of code with 4 elements. And that's because vowels are much more common in English. So you're much more likely to use, if you're trying to send a message to somebody, you're much more likely to use vowels. And so if you want to minimize the length of the message, you want to use a short encoding for frequent letters and a long encoding for infrequent letters. And so all this to say is that KL divergence has this kind of interpretation, and it's basically saying if the data is truly distributed according to P, and you try to build a compression scheme that is optimized for Q, you're going to be suboptimal. Maybe in your model of the world, the vowels are much more frequent than are much more infrequent than Q. So you have a bad generative model for text. Then if you try to optimize, come up with a scheme based on this wrong assumption, it's not going to be as efficient as the one based on the true frequencies of the characters. And how much more ineffective your code is exactly the KL divergence. So the KL divergence exactly measures how much more inefficient your compression scheme is going to be. And so if you try to optimize KL divergence, you're equivalent to trying to optimize for compression. So you're trying to build a model such that you can compress data pretty well, or as well as possible. Which is, again, a reasonable kind of way of thinking about modeling the world, because in some sense, if you can compress well, then it means that you're understanding the structure of the data, with which things are common, which ones are not. And that's kind of like the philosophy that you take if you train a model using KL divergence as the objective function. So now that we've kind of chosen KL divergence as one of the ways of measuring similarity between distributions, we can set up our learning problem as saying, okay, there is a true data generating process. There is a family of distributions that I can choose from. I can measure how similar my model is to the data distribution by looking at this object. And so intuitively, if you think about this formula, this thing is saying I'm going to look at all possible, let's say, images that could come from the data distribution. And I'm going to look at the ratio of probability assigned by the data distribution and the model. So I care about how different the probabilities are under the model and under the data distribution. If those two match, so if they assign exactly the same probability, then this ratio becomes 1. The logarithm of 1 is 0, and you see that the KL divergence is exactly 0. So you have a perfect model. If you assign exactly the same probability to every x, then you have a perfect model. Otherwise, you're going to pay a price, and that price depends on how likely x is under the data distribution and how far off your estimated probability is from the true probability under the data distribution. Yeah?
Density estimation.
Great question. The question is, okay, this looks reasonable, but how do you compute this quantity? How do you optimize it? It looks like it depends on the true probability assigned under the data distribution, which we don't have access to, so it doesn't look like something we can optimize. And we'll see that it simplifies into something that we can actually optimize. Yeah, great question.
So what would the interpretation be of the KL divergence of like T theta, like 2 lines in T theta? Just like you flipped it, what is that?
It would be more like, the question is what happens if we flip the argument of here, and we have the what's called as the reverse KL, so the KL divergence between P theta and P theta. So it would be the same thing. But in that case, we would be looking at all possible things that can happen. We would weigh them with respect to the model, P theta, and then the ratio here would again be flipped. And so we care about the ratios, but in a different sign, basically. And so that quantity would be 0 if and only if they are identical. But you can see that it kind of has a different flavor, because if you look at this expression, we're sort of saying it doesn't, what happens outside, let's say, of the support of the data distribution doesn't matter with respect to this loss. Well, if you had p theta here, then you would say, I really care about the loss that I achieve on things I generate myself. And if you think about how these models are used, that actually seems like a more reasonable thing to do, because maybe it really matters. You really want to score the generations that you produce, as opposed to what's available in the training set. But it will turn out that the nice property that we're going to see soon that makes this tractable doesn't hold for when you do reverse KL. So that's why you can't really optimize it in practice. Yeah.
So even though, say, like the KL divergence of P and Q is not equal to the KL divergence of Q and P, say if we have two sets of like P1, P2, Q1, Q1, if KL P1, Q1 is smaller than P2, Q2, would the reverse, would like a KL Q2, Q1, P1 also be smaller than KL Q2, P2?
As far as I know, not necessarily.
Not necessarily.
Yeah. Yeah.
I wonder, like, do we use other matrices, to evaluate the distance between two distributions? Let's say do integrations between the two distributions.
Yeah. So the question is, do we ever want to use other metrics? Yes. We'll see that in future lectures. We'll get different kinds of generative models simply by changing this one ingredient. So you can still define your family in any way you want, but we might change the way we compare distributions, because at the end of the day here we're saying we care about compression, which might or might not be what you want. Like if you just care about generating pretty images, maybe you don't care about compression, maybe you care about something else. And we'll see that there's going to be other types of learning objectives that are reasonable and they give rise to generative models that tend to work well in practice.
I'm just kind of curious, like for this one, for this P data P, in this kind of order, does it make more, does it have more meaning? Because the P data is really the empirical distribution, and but if you flip it, and then does it make it like less meaningful? Meaning, like although it seems to be like symmetrical, but does it make it much less meaningful because we don't really trust the Monte Carlo kind of simulation you yourself kind of imagine all of you.
Yeah. So that the question is again sort of like should the expectation be with respect to the true data distribution, or should we with respect to the model, which is what you would get if you were to flip the order here. And the quantities will be zero. Both of them will be zero if and only if you have perfect matching. But in the real world, where you would have finite data, you would have limited modeling capacity, you would not have perfect optimization, you would get very different results. And in fact, you get a much more, if you were to do the KL divergence between P theta and P data, you would get a much more mode-seeking kind of like behavior, where you can imagine sort of like if you put all the probability mass into a single, kind of like a single mode, it might look like you're still performing pretty well according to this objective. So it tends to have a much more mode-seeking kind of objective compared to the KL divergence, which is forcing you to spread out all the probability mass over all the possible things that can happen. So if there is an X that is possible under P data and you assign it 0 probability, you're going to get an infinite loss. So it's going to be very, very bad. And so you're forced to spread out the probability mass. If you do reverse KL, there is kind of like an incentive to concentrate the probability mass. So the behaviors, as you said, are going to be very different. And depending on what you want, one might be better than the other.
So we've been discussing about the flavor when we do one way of KL divergence and the flipped way. Is it kind of analogous to like precision and recall? Because in one case we're considering the denominator is the all true things, and another we're considering all the positive predictions.
Yeah. The question is, does this have the flavor of precision and recall? And yes, it has a very similar, it's not exactly precision and recall, it's a softer kind of thing, but it has the flavor of, do you care more about precision versus recall? Yeah. It's a good way to put it. All right, so we have this loss, which you can expand the expectation as something like this. And now we know that this divergence is 0 if and only if the distributions are the same. So if you can optimize this as a function of theta to make it as small as possible, it's a reasonable kind of learning objective. Measure compression loss. The challenge is, as was mentioned before, is that it might look like it depends on something. You cannot even compute it because it depends on the probability assigned to all the possible things that can happen under the true model, under the true data distribution, which you don't know. But if you just decompose the log of the ratio as the difference of the logs, you get an expression that looks like this. And now you can note that the first term here does not depend on theta. It's just like a shift. It's a constant that is independent on how you choose the parameters of your model. And so for the purposes of optimizing theta, you can ignore the first term. And so if you're trying to make this quantity as small as possible, regardless of how you choose theta, this is going to be the same. So you can effectively ignore it for the purposes of optimization. And so if you try to find a theta that minimizes this expression, because there is a minus here, the best thing you can do is to basically make this thing here as large as possible, what I have here. And this term here should be somewhat familiar. What we're saying is that we should pick the distribution that assigns basically the highest probability to the x's that are sampled from the data distribution. And so this is really maximum likelihood estimation. We're trying to choose a model that puts high probability on the things that you have in the training set, essentially. Which is the training objective that you've seen before, probably in other classes, of trying to pick parameters that basically maximize the probability of observing a particular data set. We're trying to choose parameters such that in expectation, the average log likelihood of the data is as high as possible. And so you can see that that's equivalent to minimizing KL divergence, which, as we've seen, is the same as trying to do as well as you can at this kind of compression task. And one caveat here is because we've ignored this term, it's possible to compare two models. So if I have a theta 1 and a theta 2, I can tell you which one is doing a better job. But you can never know how close you truly are to the data distribution. You can only evaluate the loss up to a constant. And so you'll never know how much better could I have been. You can't really evaluate that. And that's one of the problems here, is that we don't know how much better could we have been, right? Because there's always the shift that cannot be evaluated. And for those who have seen this in other classes, that's basically the entropy of the data distribution. And that's kind of like telling you how hard is it to model the data distribution, or what's the, how random is the data distribution to begin with? How hard is it to model the data distribution if you had access to the perfect model? That doesn't affect how well your particular model is doing, but it's the kind of thing you need to know how close you are truly to the data distribution.
As you mentioned, you could compare two models using this, but you'd only get kind of the divergence between the two, and you still wouldn't know how they compare.
So you could get, if you take let's say, you have a p theta 1 and a p theta 2, and you take the difference between the KL divergence between data and p theta 1 minus the KL divergence between data and p theta 2, the constant cancels out, and so you know which one is closer to the data distribution. But you never know how close you are. So going back to this picture, I guess what I'm saying is that, maybe it's too many. Given 2 points in here, you can tell which one is closer to the data distribution, but you never know the length of this segment. Like, you don't know how close you actually are.
Let's say you have two models and the second term is equivalent. Is there any way to objectively compare which of the two is better relative to the distribution of, let's say, other than just that 0?
Yeah, so if you have two models that achieve exactly the same average log likelihood, which one is better? Occam's razor would tell you pick the simplest one. And that's usually a good inductive bias. Okay. Now, one further problem is that, this quantity here still involves an expectation with respect to the data distribution, which we still kind of like don't have access to. So you can't still optimize this quantity. However, we can approximate the expected log likelihood with the empirical log likelihood or the average log likelihood on the training set. So remember that what we would really care about is the average log likelihood with respect to all the things that can possibly happen when you weight them with the probability given by the data distribution. That we don't have access to, but what we can approximate that by going through our data set and checking the log probabilities assigned by the model to all the data points in the data set. And to the extent that the data set is sufficiently large, I claim that this is a good approximation to the expected value. And the intuition is that you have an expectation, you have a sample average. To the extent that you take an average with respect to a larger enough number of samples, the sample average will be pretty close to the expectation. And now this is a loss that you can compute. You just go through your training set, you look what's the likelihood assigned by the model to every data point, and you try to make that as large as possible. Right? And so that's maximum likelihood learning. That's the thing that you've seen before. Try to find the distribution that maximizes the average log probability over all the data points in your training set D. And as usual, you can ignore this 1 over D. That's just a constant. It doesn't depend on theta, and so you get kind of like the usual loss function. And note, this is exactly the same thing as saying because the data points are independent, maximizing this expression is exactly the same thing as maximizing the probability of observing the data set that you have access to. So it's a reasonable learning objective. You have a bunch of data, and you're trying to find the parameters that maximize the probability of sampling a data set like the one you have access to. Right? If you take a log of this expression, the log of a product becomes a sum of logs, and then you get that these two things are exactly the same. So again, very reasonable kind of training objective. Let's find parameters that maximize the probability of observing the data set that we have access to. Yeah.
Use similar numerical methods to estimate that constant term from before, where you could like bin your data set based on X and then estimate the entropy of that.
Yeah, so the question is, can you use similar tricks to estimate this? So you can certainly estimate the expectation, but then the problem is this log probability, and that one is much harder to estimate. And you can try to do kernel density estimates, or you could even use p theta in there. If you believe you have a good approximation, then you can plug it in, but you'll never know how far off you are. So there's always approximations there.
So on the side, there's like a rule point that says like samples with p theta of x is close to 0 weigh heavily in the objective. In practice, do people do anything to like maybe alleviate that a bit? I think for discrete distributions, maybe you have a softmax that will make it a bit further away from 0. Is that something that happens like in continuous distributions, or how do you help alleviate that?
Yeah, so that's kind of like goes back to what we were saying. What is this model doing? Like it's trying to make sure that if something is possible happen in the training set, you're going to be forced to put some probability mass there, which is a good thing, right? You're going to be forced to spread out the probability mass so that the entire support of the entire data set is covered by your model. Now the problem is that you always have finite modeling capacity, right? So if you put probability mass there, might be forced to put probability mass somewhere that you didn't want to, and maybe then your model will hallucinate weird stuff that was not in the training set, but you have to generate them because you're forced by this objective to spread out the probability mass. Again, back to precision recall, you need to have a very high recall. Like everything in the training set has to be non-zero probability. And as a result, maybe your precision goes down because then you start to generate stuff that should not have been generated. So that's kind of like the takeaway of that line. Cool. Now, why does this work? That's an example of like why can you approximate this expectation with this sample average? This is something that is basically a Monte Carlo estimate. You might have seen it before. The idea is that if you have an expectation of some function, there's a random variable x, there is a function g of x, you want to get the expected value of g of x, which is just this thing. You can approximate this by just taking, so the true thing would look at all the things that can happen and it would weight them with the probability under p. Alternatively, what you can do is you can just generate t scenarios, t samples, and look at the average value of g under these t samples, and that should be a reasonable approximation, right? You kind of like approximate the expectation by looking at the value of the function on these t representative samples. And this g hat is a random variable because it depends on these samples, x1 through xt. And so, but it has good properties in the sense that in expectation, it gives you back what you wanted. So although this g hat is now a random variable, in expectation, that this random variable has the right value, which is the true expectation of the function, the thing you wanted to compute. And the more samples you get, the better the approximation is. So although g hat is random, as you increase the number of samples t, g hat converges pretty strongly to this expected value. So the more samples you take, kind of like the less randomness there is, and the more likely you are to get close to the true answer you're looking for, which is the expectation of the function. And the variance also goes down as the number of samples increases. So you have a random variable that in expectation gives you the answer you want, and as you increase the number of samples, the variance of these random variables becomes smaller and smaller, which means that your approximation becomes more and more reliable. The less unlikely you are that the estimate you have is wildly off. And that's exactly what we're doing here. We are approximating, this expectation is a number, it's not random. We're approximating it with a quantity that depends on the training set. So different training sets would give you different answers. But if the training set is sufficiently large, this sample average would be very close to the expectation. And the larger the training set is, the more likely it is that this sample average that you get on the data set is actually going to be pretty close to the true expected value that you care about. Cool. So, and we'll see this kind of idea come up often, this idea that there is an intractable expectation that you have to deal with, and you're going to approximate it using samples from the distribution. It's a pretty convenient way of making algorithms more computationally tractable, essentially. Was there a question? Okay. Right, so now back to learning. I mean, you've probably seen maximum likelihood learning in examples like learning the parameters of a Bernoulli random variable. So let's say you have two outcomes, head and tails. You have a data set. So you've seen that you flip the coin 5 times, and the first 2 times were heads, then you have a tail, then a heads and a tail. You assume that there is some underlying data distribution that produced the results of this experiment that you did with 5 tosses of the coin. And then you model all these Bernoulli distributions. And then again, you just need one parameter to describe the probability of heads versus the probability of tail. And then you could try to fit. And you try to find a model of the world that is as close as possible to the true data generating process. For example, you might see that there is 3 heads out of 5 of coin flips, and then you try to find a good model for this kind of data. And the way to do it is maximum likelihood. So in this case, p theta would be really, really simple. It's just a single kind of like Bernoulli random variable. You have one parameter, which is the probability of heads. 1 minus theta is the probability of tails. And then you have your data set, which is 3 heads and 2 tails. And then you can evaluate the likelihood of the data. And it's just that expression. So you have theta, theta, 1 minus theta, because the third result is a tail, and so forth. And now this is a function of theta. As you change theta, the probability that your model assigns to the data set changes. And if you plot it, it kind of has the shape. And then maximum likelihood would tell you pick the theta that maximizes the probability of observing this particular data set. And that basically corresponds to trying to find a maximum of this function. And in this case, what's the solution? Yeah, 0.6, right? In this case, you can actually solve this in closed form, and you can work out what is the optimal theta, and it's going to be 0.6. And so we're basically going to do the same thing now, but for autoregressive models. So this is the same idea. You have, except that now theta is very high dimensional. It's all possible parameters of a neural network, but the y-axis is the same. It's basically the probability that your model assigns to the data set, and then you try to find theta that maximizes the probability of observing the data set that you have access to. And the good news is that in an autoregressive model, evaluating likelihoods is relatively easy. If you want to evaluate the probability that the model assigns to a particular image or sentence or whatever, the probability of x is just given by chain rule. It's the product of the conditional probabilities. And so evaluating the probability of a single data point is very easy. It's exactly the same computation we did before when we were trying to do anomaly detection. You just go through all the conditionals and you multiply them together. And how to evaluate the probability of a data set? Well, the probability of the data set is just the product of the probabilities of the individual data points. And the individual data points are just obtained through chain rule. And so, again, it's all pretty simple. If you want to maximize the probability of observing the data set that you have access to, you can also take a log, and you can maximize the log likelihood. And you get an expression that when you can turn the log of a product into a sum of logs, but we no longer have a closed form solution. So before, for the Bernoulli coin flips, you all knew the answer is 0.6. If you have a deep neural network here, you no longer have a closed form way of choosing theta, and you have to rely on some kind of optimization algorithm to try to make this objective function as high as possible. You negate it and try to make it as small as possible. And so you can, for example, you can use gradient descent. So that's the objective function that we're trying to optimize. And if you take a log, I guess it boils down to this, which is much more natural. So you go through all the data points, you go through all the variables in each data point, and you look at the log probability assigned of that variable given all the ones that come before it in that data point. So equivalently, what you're doing is, remember that these p-neural here are basically classifiers that try to predict the next value given everything before it. And so this loss is basically just evaluating the average loss of all these classifiers across data points and across variables. And so again, basically minimizing KL divergence is the same as maximizing log likelihood, which is the same as basically trying to make these classifiers perform as well as they can. They should do a pretty good job at predicting overall data points j, overall variables I. They should do a pretty good job at predicting the next variable given all what they've seen so far for that particular data point. And so all of this is basically boiling down to let's try to make these classifiers that predict the next variable given the ones before it as efficient, as good as possible in terms of the essentially cross entropy. So one way to do it is you can initialize all the parameters at random, and then you can compute gradients on this loss by backpropagation, and then you just do gradient ascent on this thing. It's non-convex, but in practice, basically that's how you would train all these models, and it tends to work pretty well in practice. One thing to note is that as written, this quantity involves a sum over an entire data set. Like if you want to know what's the effect of changing the parameter of one of these classifiers, so you want to get the gradient of the loss with respect of, let's say, theta I, where theta I is basically the parameters of the ith conditional. You would have to sum over the whole data set to get this gradient, which would be, of course, way too expensive because you would have to go through the whole data set to figure out how to adjust the parameters of your classifier. And that's tricky, but here I'm actually, okay. The good news is, okay, each conditional can be optimized separately if there is no parameter sharing. In practice, there is always parameter sharing. The challenge is that you have this big sum over all the data points in the data set. But again, what we can do is we can use a Monte Carlo estimate. So instead of going through the whole data set, we can try to estimate what is the gradient just by looking at a small sample of data points. Just like before, we were approximating an expectation with a sample average. We can think of this sum over m over all the data points. We can multiply by m and divide by 1 over m. And then we can think of this sum over m, 1 over m, as an expectation with respect to a uniform distribution over the data points in the data set. And so you can write down the gradient as the expectation of the gradient with respect to a uniform distribution over the data set. And so far we haven't gained anything, but now you can do Monte Carlo. You can approximate this expectation by taking a bunch of samples and evaluating the gradient only on those samples. And that's basically stochastic gradient descent or mini batch, where you would basically select a small subset of data points. You will evaluate the gradient on those data points, and you would update your model accordingly. And so we see another layer of Monte Carlo simulation or Monte Carlo estimate, where instead of evaluating the full gradient, you evaluate the gradient on subset of data points to make things scalable. And what else? Yeah, the other thing to keep in mind is that, well, there is always the risk of overfitting that sort of like came up before. If you just blindly optimize that objective, you could just memorize the data set. So if if the data becomes the model, you're going to perform pretty well at this prediction task, but that's not what we want, right? So we don't care about the performance on the data set. We care about performance on unseen samples that come from the same distribution as the one we've used for training. So the same problems that we've seen when you train a machine learning model apply here. Blindly minimizing this loss might not do what we want, because you can do very well on the training set, but you might not be doing well in general. You might not be generalizing. And so what you would need to do is to somehow restrict the hypothesis space or regularize the model somehow so that this doesn't happen, so that it doesn't just memorize the training set and it doesn't so you don't get this kind of like overfitting behavior. And the problem, and then you get the usual kind of like bias variance trade-offs, where if you limit the model too much, if you restrict the modeling capacity too much, instead of using deep neural network, you use logistic regressions, or you make very strong kind of conditional independence assumptions, your modeling capacity or hypothesis space becomes too limited, and you might not be able to do well at minimizing that loss on the training set. And this is basically biased because it limits how well you can approximate the target distribution, even if you could optimize as well as you could. And then the trade-off here is that if you choose model families that are too flexible, then you encounter the other issue, which is variance. So your model might be fitting too well. It might be fitting even better than the true model that generated the data. And even small changes to the data set could have huge changes to the parameters that you output. And that's variance. So you kind of like want to find a sweet spot where you balance the effect of bias and variance on the performance of your model. And kind of like visually, I think this is an example. Let's say that you have a bunch of data points and you're trying to fit a curve, trying to predict y from x. If you choose a very simple kind of space of possible relationships, like all linear models, you can do very well at fitting, but somehow if the model class is too simple, you're not going to be able to capture the true trend in the data. And so the bias here will hurt you too much. So it kind of underfits. If you choose a very flexible model, lots of parameters, you're going to be fitting the data set extremely well, but you can see that perhaps it's too flexible, the model. If you were to change one single data point a little bit, the predictions would change drastically. And that's maybe overfitting. And so you want maybe that sweet spot where you have a low degree polynomial that fits the data a little bit worse than this high degree polynomial, but it kind of like will generalize and it will perform okay in practice. And yeah, question?
Because when we train our models, we will set those hyperparameters fixed, and then we train the model, right?
Yeah.
So it's like the case you show here. We say this is a polynomial with order 3. Is there like any way for us to, turn the model parameters into trainable, or just have a very elegant framework?
Well, yeah. So there's a few things you can do. One is to prevent overfitting is you could be Bayesian, but that's very hard computationally. Another thing you can do is you can try to do kind of cross-validation, where you kind of like keep some held out data to evaluate the performance of your model. And if you see that there is a big gap between the performance that you had at training time versus what you had on the validation set, then you know you're overfitting, and so maybe you want to reduce the complexity of your model. And so, yeah, one thing you can do is you can reduce the complexity of your neural networks, reduce the number of parameters, share parameters, kind of like makes this set smaller in some way. Another thing that was mentioned before is you could try to use some kind of like soft preference for simpler models, so that if you have two models that fit the data equally well, they achieve the same loss. Maybe you have a regularization term that says prefer the simpler one. Maybe the one with fewer parameters, or the one with where the magnitude of the parameters is smaller. And the other thing is what I just mentioned. You can always evaluate performance on some held out validation set. This is actually what people do in practice. And you can check. If there is a big gap between training and validation loss, then you know that you're probably overfitting. And maybe you want to reduce the size of this set, or you want to do something to prevent that overfitting. And yeah, I think that's probably a good place to stop. I think training conditional models is pretty much the same thing.